Hello. Before starting the main lecture, I'd like to announce my plan from now on. So we have 8 more classes to go, including Thursday today, October 29th. So this is the reason why I'm telling you this plan is because it gets too long. I already posted 5 videos, recorded 5 videos, and I have still have one remaining example. So, and also I have to post the homework walkthrough. So then my plan is, so this was the original plan. I planned to finish one chapter in a week, in 2 classes. Then we have one extra class. So the last class is on extra. So my plan is these classes. I'm going to stick to this schedule, one chapter a week. It's nice schedule, and also being continuous is important for your understanding. So I am going to cancel this, and instead there will be cancel typo. I cancel. So I am going to cancel. There will be no videos posted in the last week. Enjoy Thanksgiving. But I will go over time. I may post more videos than usual in these classes to keep pace with the plan. So please excuse me today's long videos. The videos there may be too long, but it's, it's to finish. It's nice to finish one chapter in a week, and it's only like 7 or 8 slides left. This is the last example from this chapter, and I'm going to consider an interesting example about COVID-19 vaccine. Of course, the numbers are not realistic numbers. The numbers are fake. Just it's an imaginary data, an imaginary setup, and I have no expert knowledge about this medical science. So don't believe in the content. Just consider it as a numerical example. Suppose that you developed a vaccine for COVID-19. Congratulations, you are now rich. You believe that it builds antibodies with probability 80%. So a vaccine does not guarantee a full antibodies for everyone. So there is still some probability. That's what I know. Maybe I'll think I'm correct. So anyhow, suppose that it's successful with 80%, and you want to test this probability. This probability 80% is the parameter of your interest. And so the hypothesis we are interested in is whether P equals to 80% or not, where P is the probability of having antibodies after vaccination. So if you randomly choose a person who was vaccinated and check if he has antibodies or not. So let's think about the data. The underlying data takes this form. When you choose a random person who gets the vaccine, check one success if the person has antibodies and 0 otherwise. So that means the underlying variable is a binary variable. It's a binary distribution, and in this case, the P, the parameter of interest P, is interpreted as the probability of success, but it is also its mean. So we may use the same hypothesis testing method for the mean. So far, we only considered population mean, and that same method, can be applied to this parameter, which is even if it's a probability. So, but there is one thing you have to be careful about, that is the standard deviation. So far we just in the binary distribution from chapter 5, yes, we learned that the standard deviation is given by p, the parameter p. P already determines the standard deviation too, not only the mean but also the standard deviation. So you have to use this formula in the hypothesis testing method. And let's see how we do it. As usual, we have to believe that the null hypothesis is true until it is proven wrong. So then we have standard deviation of x is square root of p times 1 minus p, and the null hypothesis implies that p is 80%. So p is 80% implies standard deviation is 0.4. So this is your standard deviation. Standard deviation is 0.4, and we use this standard deviation to calculate the null distribution. Remember, the reason why we are using, so it's very confusing because the standard deviation is not calculated from the sample, but calculated from the null hypothesis. Null hypothesis, the reason why we are using the null hypothesis to calculate the standard deviation is because that's the definition of the null distribution. The null distribution is the sampling distribution when the null hypothesis is true. So ideally, if the null hypothesis tells you what is the standard deviation, that is your standard deviation. But so far, in the previous examples, we could not obtain the null hypothesis does not say anything about the standard deviation. It only mentions the mean, about the mean. So we had to calculate standard deviation from the sample, from the data, because the null hypothesis did not say anything about that. However, in this example, due to the property of a binary distribution, the null hypothesis kindly determines the standard deviations in this way, which is actually very nice. It is nice because already everything from the null distribution is fixed, except for the sample size. So as long as you have the sample size, so here originally we used S. S was the standard deviation calculated from the data. But now we don't need to use the data to fix this guy. It is already given by this form. And so far I did not mention anything about data. I just described the hypothesis and how the data look like, how the distribution look like, and what's the null distribution. Now you can go survey and collect data. And suppose that you observe 100 cases, 100 people have the vaccine, and you study their, say, blood, and antibodies were found from 75 out of 100. Then find the p-value. The formula is the same except for this guy. So use the same formula, calculate t-statistic, and use the p-value, normal distribution. Just in case if you wonder what's the sample mean, you observe 100 and out of 100, 75 successes, then the sample mean equals sample proportion of success. So sample mean equals 0.75. Do the math. Pause the video if you need. 3, 2, 1. T-statistic is sample mean minus the belief and the standard deviation square root of n. Remember, this standard deviation is now 0.4. It's actually square root of p times 1 minus p. Other than that, it's standard formula. And p-value formula is the same. There is no difference. Use the t-statistic and plug that in and calculate probability outside the p-value, the t-stat. Then you get 21%. So, using the p-value, find significance levels that reject the null hypothesis. It's simple. 3, 2, 1. Yep. The answer is no, none. So, remember, 10%, for example, significance level of 10% means you are going to reject top 10% suspicious outcomes, top 10% unlikely outcomes, but p-value is 21%. So that means your outcome, your observation is ranked at 21%. So you are rejecting this much, but yours is here. So none of them. So remember, you reject the null when p-value is smaller than the significance level. In this case, no among these. Then now find the critical values at 5% now. Again, the idea is the same, formula is the same, except for the standard deviation. And pause the video and do the algebra. 3, 2, 1. First of all, okay. So 5% implies z-value of 1.96, like familiar number. So plug in 1.96 here, and the belief is 80%, which is 0.8, standard deviation 0.4, and square root n is 10. So easy, right? So this shows that you believe that the probability is 80%, but you allow a margin of plus minus 7.84%, right? So that's what it means. And then can you reject the null hypothesis? The sample mean was 75%. Answer 3, 2, 1. Yes. No. Excuse me. No, you cannot reject the null hypothesis because so the critical values is from 72 to 87, but your observation is 75%, which is around here. So it's in between greater than the lower critical value and smaller than the upper critical value. So it is within the acceptance region. So you don't reject the null hypothesis. Finally, compare the critical values with the confidence interval. What's interesting here is, so formula for the confidence interval is this, and x bar is 0.75 in this way, and the major difference is the standard deviation. We considered a similar example in the previous chapter, and the standard deviation follows the same formula, p times 1 minus p, but now p is from the sample. Because when you estimate the parameter, you have no belief. Everything has to be from the data. So your standard deviation is calculated from the sample probability, sample mean 0.75. So the standard deviation is different. It's very tricky. So this is it. This is the end of the chapter. And I'm going to continue hypothesis testing about more additional topics in chapter 10. And as I said, this is very confusing and very exotic concept, very unnatural way of inference. So I want to grasp the main intuition, not the formulas. Formulas are easy, too simple, but the idea is not that easy. Thank you for watching this, and see you next week.